Good afternoon, all. Today, we are happy to welcome Professor Saketh Saurabh. He is one of the experts from the area of theoretical computer science. Professor Saketh is a professor at Institute of Mathematical Sciences, Chennai, India. He is also affiliated to the Department of Informatics, University of Bergen, Norway. He did bachelor and masters from Chennai Mathematical Institute and PhD from Institute of Mathematical Science. His area of research includes parametrized complexity, moderately exponential time algorithms, graph theory, approximation algorithms. Professor Saketh is also an author of 2 books in the area of parametrized complexity. He has published over 400 research papers, and his contributions to the area of theoretical computer science has been recognized by a number of awards, including the ACM Early Career Research Award 2020. And today, he will be talking on the topic parametrized approximation algorithms. I request all participants to give your full attention and share your questions in the chat, or you can unmute and ask questions. Let's get started. Over to you, Professor.
Thanks a lot, Bursa, for such a flowery introduction. Just my suggestion to all the participants that please treat it as a normal class. And if you do not understand something, or if I'm going too fast or slow, please, you can just unmute yourself and ask question. And if you don't feel like that, so as Bursa said, you can put in the chat. I will try to see it. If not, then someone will let me know. Or if still you see that your questions are not answered, please unmute yourself and just say, hey, I put up a question in the chat. Can you answer that? Okay. So with the parameters of the lecture clear, let me tell you that what I plan to do in today's lecture and the lecture after that is that yesterday, if I noticed, yesterday Pradisa taught you what FPT is, and she told it's like basic techniques like branching, kernelization, right? And she briefly talked about iterative compression. Okay. So our objective will be twofold. One thing is that we will add some more tools to this list, as well as explore different paradigms. Explore different paradigms, okay, like approximation, streaming, dynamic, you name it. Okay, so that is an overall idea of the lectures. So the first thing, if you recall FPT, what was it? So in FPT, in general, what happens is that we have input, okay? We have an instance, a parameter k, okay? And parameter is k, and the question is, suppose I have some language L. Question is, does I comma k belong to language or not? Okay. And just to be specific, my language is going to be vertex cover, right? So what are the instances of vertex cover? G comma k, G has a vertex cover of size at most k. I hope all of you know the definition of vertex cover by now, so I'm not going to redefine the definition of a vertex cover, okay? But now what I mean, so what does the algorithm actually does in the vertex cover? So algorithm for vertex cover, it takes an instance G comma k, and it tells us, it tells you yes, meaning G has a vertex cover of size at most k. When it says no, let's say no, what is the meaning of that? It says no. We can immediately say that G has no vertex cover of size at most k. Okay. Now, imagine that I would like to make this definition for vertex cover, but in terms of approximation. Okay. And so if you look at the only difference between classical problem and the parametrized problem was that you still want to answer the following decision question. But classically, while we allowed you to have a running time of the form, what did we allow you to have? Just n to the power big O of 1, where big O of 1 could be n to the power 2, n to the power 3, n to the power 100, whatever. But in parametrized complexity, I give you additional power and say, hey, you can actually take any algorithm with running time n to the power big O of 1. So for example, f of k could be 2 power k, which you might have seen for the vertex covered, or maybe 2 power k, so on and so forth. But that's a basic difference between parameterized algorithms and classical algorithms, is that classically, we only allow polynomial time for solvability, but in FPT, we allow a dependence on the parameter f of k, but the dependence on the input or should be purely polynomial. Okay. Okay. So just to motivate you people, and let's see how many of you know this. Okay. How many of you heard of the problem called subset sum? What is the subset sum input? Input is n items, right? A1, A2, AN, and an integer W, and an integer W. And the question is, does there exist a subset of integers, or you can say some I subset of 1 to n, such that if I sum the element j in I, aj, that is equal to W. So, okay. So if you have seen this problem before, can you put say yes in the chat? Okay, then I will know that you know it. So if you have seen the problem, yes, great. Okay. Yes. Yeah. So this will be, so we will follow such protocols just for me to know whether you have seen this or not. Okay, great. Okay. So does anybody know any algorithm for subset sum? Candidates for a knapsack problem, meaning? Ishwaran?
A subset problem, isn't it like a knapsack problem?
It is like a knapsack. It is a knapsack, like it is like a knapsack problem only. It's like, yeah, but in knapsack you also have like, you not only have to maintain the constraints of capacity, you also have this, like, you would like to gain something, right?
Utility,
like,
yes.
Utility, right? So yes, in some sense, it is a simplified version of knapsack problem.
Okay. Okay. Thanks.
Yeah, welcome. Right. So my question is, have you seen this algorithm before in your this algorithm? How many of you seen this algorithm in your algorithm course? Anybody? Yeah, put 1. That's great. If you have seen this, put 1. Yeah, dynamic programming, all of that. Yes, all of you are right. Okay. But notice that if I treat W, okay, as kind of, part of parameter, then what is the value of W? So like to give W, all I need is log W bits, right? So this is my K. So my parameter is W, but not in in-array, in binary. If I look at then this algorithm is nothing but order n to the power 2 power k, right? Yeah, this is exactly why you call pseudo-polynomial time algorithm, because like the reason why it is pseudo-polynomial time, because it is polynomial in the unary encoding, but if I treat W as a binary encoding, then it is nothing but an algorithm which is FPT in the parameter W encoded in binary. Okay, so that's a base. So this is a classical or simple FPT algorithm that all of you have seen in your own classical text, right? It's an FPT algorithm parameterized by W. Okay, right. And we do not hope to have an algorithm. We do not hope to have an algorithm for this with running time n to the power log W big O of 1. We do not hope to have such an algorithm, right? Unless P is equal to NP, right? Because for larger values of AI, because AIs can be much larger than polynomial, because I can have AI which is like 2 power poly n, and still I use only poly n bits, right? So in numeric problems, this exponential encoding of numbers is what makes the problem NP hard or something of this nature, okay? Or whatever hardness. Otherwise, for many of these problems, you can get what people have been calling pseudo-polynomial time algorithm. Okay. 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 So having said this, how many of but if I allow you that fine, okay, knapsack would have been easier, but what kind of algorithm we will be dealing with today is that slightly different kind of algorithm. So for the vertex cover, what I will mean is the following. Vertex cover, let's say I want to give you 2 approximation for vertex cover. But let me first define what I mean by 2 vertex cover. So my input is going to be G comma K, okay? My parameter is going to be K, and my question is going to be if G has a vertex cover of size at most K, then, okay, then you can return vertex cover of then you can return vertex cover of size at most 2K. That's perfectly fine. Okay. Now, so algorithm needs to have a guarantee that if the graph has a vertex cover of size at most K, then you are able to return vertex cover of size at most 2K. Okay. Now, if G does not have vertex cover of size at most K, then you can return no. Okay. So if you look at picturesquely, what is the meaning of this? Notice. If I draw this boundary, okay. So what is this meaning of this? It tells us, look, if you do have a vertex cover of size K at most K, okay, then you must return a vertex cover of size at most 2K. But imagine that if the vertex cover would have been size 2K, then what will my algorithm will have to do? Because whatever happens, right? Whatever happens, I don't know whether like I cannot return a vertex cover of size at most 2K. So if the input is really of this nature, then I must return an solution. I will definitely say no in this algorithm, in this region, okay? In this region here. But when the value of K is somewhere here, okay, I may not return anything. I mean, I could, so look, I could say that like, okay, fine, like I'm allowed to say no, but you are also allowed to say yes, like somewhere here. So if you do have a vertex cover of size at most K, then if you do have a vertex cover of size at most 2k, and this is exactly how most approximation algorithm works, right? So if it has size at most k, then you must return something. If it has a size strictly more than 2k, you must return no. But in between, when the vertex cover is between k and 2k, you could return anything. So for example, looking at a solution, I cannot determine whether I do, like original graph has a vertex cover of size at most k or not. Okay. So we would like to determine, what is our goal? So I want to solve, give you a 2 approximation for vertex cover. Okay. So that was definition with respect to 2. But suppose if I put this definition and I say, look, let's call it an alpha approximation algorithm. It will mean that then you must return a solution of size at most alpha k. And if G does not have vertex size at most k, then you can return. Okay. Now notice then this threshold where I can say is this remains the same. Okay. Now my question to you, do you know any 2 approximation for vertex cover? Anybody? Has anybody seen any factor 2 approximation for vertex cover anywhere? Was there not a lectures on approximation algorithm? ILP formation, very good. What about have you seen this approximation? Greedily find a maximal matching. Okay. Greedily find a maximal matching. Okay. Okay. Say M. Let C equal to vertex set of M. Right. Now I can say, hey, if C is at most 2k, great. Okay. Otherwise, C is more than 2k, which implies maximal matching is more than k. Okay. Return no. Right. So I can use this known factor 2 approximation to give a factor 2 approximation for vertex cover in a polynomial time. Is that clear to you, all of you? If yes, can you put 1 if this algorithm is clear? So what did I do? I find a maximal matching. If the size of the maximal matching is more than k, strictly more than k, you say there is no vertex cover of size at most k. Okay. Why? Why is this true? Because if you do have a maximal matching of size more than k, then you can't have a vertex cover of size at most k. Why? Because every vertex cover must pick at least one vertex from each of the matching edges, right? So it means that any vertex cover must have size at least the size of the maximal matching. And hence, if I do find a maximal matching of size greater than k, then I can return there is no vertex cover of size at most k. If maximal matching has size at most k, then you take both the endpoints of this maximal matching and return as a potential vertex cover of size at most 2k. And why it is a vertex cover? Because look at any other edge. Because it's a maximal matching, you cannot have an edge which does not intersect with the endpoints of your matching. And that is why it proves that if I pick up all the endpoints of my maximal matching, then that will constitute a feasible vertex cover of size at most 2k. Is that fine? Everybody, is that okay? If okay, please put 1 in the chat. Okay. So now, Disha would have taught you a vertex cover algorithm yesterday. What was the running time? Anybody? What was the algorithm doing? It would have tested you whether graph has a vertex cover of size at most k or not. Do you recall that algorithm? Great. Okay. So all of you agree that you have seen an algorithm with running time 2 power k. Okay, so we have this algorithm 1. We have this algorithm 2. Okay, now, but look, I mean, if I give you a power of FPT running time, then maybe let's ask ourselves, can we get, say, 1.5 approximation for vertex cover? Which is, say, what should be this? And I should take running time better than 2 power k. Can you think of any algorithm? Right? So we have a simple factor 2 approximation, which greedily finds a maximal matching, returns an endpoint, and that's a factor 2 approximation. I do have an exact algorithm that returns me a vertex cover of size at most k in 2 power k running time. And now I would like to combine these two algorithms to design an 1.5 approximation for vertex cover. So any idea how we could have gone about it? Okay. Idea is simple. Okay. Very simple. So let's see 1.5 approximation of vertex cover. Okay. Okay. So what I'm going to do is the following. Okay. What I'm going to do is the following. Step first, compute a maximal matching. Okay. So I computed maximal matching. Okay. This is my first step. I computed a maximal matching. If cardinality of M is more than k, return no vertex cover of size at most k. Okay. So let's assume without loss of generality is that M is less than equal to k. This we know. Okay. So imagine that I pick up half of this maximal matching, not all. I only pick up, say, k by 2 edges of the maximal matching. Okay, let's call this set X. Okay, now these are maximal matching edges. Okay, now let Vx vertex set of X be W. What is this? Vertex set of matching edges in X. Okay, now let's ask ourselves, what can we say about the vertex cover of G minus W? Anybody? Can you make some conclusion about vertex cover of size, vertex cover of the graph G minus W? So just so that you have everything, this is what it is. Anybody? Feel free to unmute yourself and let me know. Anybody? Okay. So if I did have a vertex cover n minus k almost. Well, look, if I was looking for a vertex cover of size at most k in my original graph, notice that, look at, let's make this assumption. If G has a vertex cover C of size at most k, then what can I say about C intersection X? C intersection, not X, C intersection W. Okay. Can you say something about C intersection W? What is C intersection W? Is at least how much? Look, C is a vertex covered, then from every edge in X, which is a matching, C must be picking at least one endpoint from at least one vertex from each of the matching edges. And the size of X is exactly k by 2, okay, which implies that C intersection W must be at least k over 2. But what we know? We know that this implies that C minus W is also a vertex covered of the graph G minus W. And what is the size of C minus W? Is at most k over 2, because C intersection W was at least k over 2. Actually, right? We know that C intersection W is at least k over 2. So we know that G minus W, the graph which we constructed, has a vertex cover of size at most k over 2. So now what I will do as a step 2, I will run algorithm from yesterday for vertex cover on the parameter, what will be G minus W and k over 2. Okay. Now I have two cases. It returns yes, it returns no. If it returns no, it implies that G has a vertex cover of size at least k. Great. If it returns yes, it means I have k. Okay. Sorry, I have got a solution of size k by 2. Now notice that if I take the set W, let's suppose it returned the set S of size k by 2 such that G minus W minus S is an independent set. Okay. Which implies that we have got vertex cover for G of size how much? Let's say W plus S, where W is bounded by 2 times k by 2 plus size of S is bounded by k by 2, which is 1.5 k. Great for us. And what is the running time of the algorithm? Well, the first step, step 1, this is poly time. This is poly. Step 2, 2 to the power k over 2, because you ran the algorithm with parameter k over 2. So the overall running time of this algorithm is going to be 2 to the power k by 2 times n to the power big over 4. Is this clear to all of you? If yes, put 1. If not clear, please feel free to ask, because it's the simplest of the algorithm we would have seen today. Okay. So the idea was very simple. What did we do? We said, look, we found a subset of obstructions or the edges with the property that it had a guarantee that it provides me locally a factor 2 approximation, but we did not run this locally factor 2 approximation in all the graph. We found a portion of graph, removed it, but we had a guarantee that optimum solution also has decreased in my reduced graph. And then we ran the parameterized algorithm with a smaller parameter. And notice, by the way, there is nothing about running yesterday's algorithm here. Okay. Here I should say run the best FPT algorithm for vertex cover. Right? Run the best algorithm for vertex cover. So then the running time will be best base of the algorithm to the power k by 2 times n to the power big O of 1. And the best base for the vertex cover is roughly 1.28. So actually our algorithm will run in time this much. Next question. Where did we use alpha equal to 3 by 2 in our approximation algorithm? Can we do better? Yeah, you could do better. I mean, look, you can get, so there's a very nice boundary here. Okay. So look at here, alpha equal to 1, like a factor 1 approximation, then it will be like 2 power k algorithm. Okay. Alpha equal to 2, it is, so let's call it n to the power big O of 1. And by the time if you're happy with factor 2 approximation, n to the power 1 remains, and this 2 becomes 1 power k. Right? Okay. Just like, okay. And notice that for alpha equal to 3 by 2, our algorithm had running time 2 to the power k by 2 and n to the power big O of 1. So it appears that maybe if we want an approximation which is close to 1, like alpha equal to 1, because then alpha k is nothing but k, then we are going closer to 2 power k, and as the approximation factor becomes worse and worse, running time improves. And that is very understandable. So for example, what would have happened if you would have taken rather in the beginning, you take this matching and you only take x some k by 4 of them, right? Then you would be spending how much? Notice then the factor 2 approximation, because you take both the endpoints, it will give us 2 times k by 4 plus, but now the parameter which is left for everybody else is like 3k over 4. So what is this? This is k by 2 plus 3k by 4. So this is like, I think 5 by 4, no? Yeah, it is 5 by 4k, which is better than 3 by 2. But the running time will be now 2 to the power 3 by 4k. Okay. So if I put alpha equal to some 5 by 4, then I will get 2 to the power 3k by 4 times n to the power big O, right? So as we are getting closer to 1, we are spending more and more time. And you can prove that if you take more from here so that you reduce, for example, if I took here, not k by 4, but 3k by 4 edges, then how much will I spend here? Well, I'm taking 3k by 4 edges, then I would have spent 1 by 5k, but I also have reduced my parameter by 3k by 4, so k by 4 more. So I will get here, like it will like alpha will be like 1.75, but the running time will be is like 2 to the power k over 4. So like there's a whole range of approximation algorithm you can get. And there is a very good trade-off between what approximation ratio you're able to achieve and how much running time you are giving. Okay? Okay. So I hope, I mean, you can derive a formula for the running time in terms of like what approximation. So for example, you say, hey, if I'm going to get a factor alpha approximation, then I will have 2 to the power some running time and things of this nature you can derive. Okay. Is that clear? Okay. If it is clear, then I will move to different concept. Okay. Okay. Good. Okay. Okay. So what fun, I mean, if we are always solving FPT problem when what fun if we are always solving FPT problem when combining with approximation. Okay, no fun. So actually we also have a concept of problem not belonging to FPT. Okay, does people know, like, have anybody heard the concept of not belonging to FPT? Like, problems are hard, meaning, well, we cannot have f of k n to the power big O of 1 time algorithm unless sun ceases to exist. Okay, it just basically means like some unlikely conjecture happened. Please don't take it literally. Some unlikely collapse of complexity theory. Okay. I mean, a roof falling on the head just now has much larger probability that some of these conjectures to be true. Okay, so in that sense. So anybody has heard of problems which may not admit an FPT algorithm? If you have seen it before, you can put +1. If not, put 0. Okay, someone said graph coloring. Let's try to understand them. Okay. Okay. So let's see, graph coloring. That's a very good example, but let's see the reason why that is hard. Okay. Input is g comma k. Parameter is k. Question: is g k colorable? Meaning, can we find a function from vertex set G to integers 1 to k such that for each edge u comma v in E of G, f of u is not equal to f of v, right? Okay, so this is basically what means colorable. Okay, now why is this problem? And I'm hoping to design an algorithm with running time f of k n to the power of big O of 1. What happens if we design such an algorithm? What goes wrong? Anybody? Please feel free to unmute yourself and answer. In the worst case, you will make a mistake. All of us make mistakes. It's perfectly fine. So let's just ask ourselves, okay, how many of you know the fact that 3 coloring is NP complete? For a fact. I'm not even saying you know the proof, like for a fact, that if I replace k equal to 3, then deciding whether a graph can be colored with 3 colors so that there is no edge which is monochromatic is NP complete. How many of you know this? Just as a fact, I don't even care if you know the reduction or not. Very good. I'm very happy that several of you know. Now ask yourself that if the graph coloring, okay, just for you to be able to see everything. If for graph coloring, we had f of k n to the power big O of 1 algorithm, then for k equal to 3, what will this imply? What is its running time? What can you say about f comma 3 n to the power big O of 1? This is still polynomial, right? This is still polynomial. Okay, this is still polynomial. So graph coloring parameterized by k can't have f of k n to the power big O of 1 algorithm unless unless p equal to np. In fact, if you look correctly, we can actually say something more strong. In fact, we can say that, hey, not only this, in fact, I can't even have an algorithm with running time n to the power f of k for any function f. Why? Because n to the power f of 3 is also n to the power big O of 1, right? So unless polynomial time fails, right? So unless polynomial time is, unless p equal to np, we do not hope to have an algorithm for graph coloring parameterized by number of colors with running time n to the power f of k, right? So this is our first non-trivial, say, lower bound results in FPT complexity. Okay. Okay, so having talked about graph coloring, let's do a fun thing on graph coloring. Okay. Okay. What about two coloring? Is it in P or NP? Anybody? Poly. Why? One word algorithm. Yes, polynomial. Agreed. One word algorithm. Bipartite. Yes, very good. Bipartite testing. So what is one word for this algorithm? What one word can you tell me that convince me that, hey, this is an algorithm? Bipartite testing and two colorability is same. Correct. I agree. Correct. The right word is BFS. You do the BFS, okay, and look at the odd layers and even layers. If the odd layers and even layers are independent set, then you have found your two coloring, happy. And if there's an edge in any of these layers, then you can use that to construct an odd cycle. Excellent. Bipartiteness testing, right? And BFS. So in fact, linear time. Okay, very good. Okay. Okay. Now I change myself. Let's say I ask myself on planar graph. Is 4 coloring in planar graph poly or NP complete? I give you a 4 color. I give you a planar graph, and I want to know whether this graph is 4 colorable or not. Like, can I use 4 colors to check whether my planar graph is this question poly time? Okay, NP complete. If you believe him, put +1. If you don't believe him, put 0. This is just a voting. A lot of people believe him. At least you can vote. I mean, vote in mass. There are like 37 people. I only see 4 votes. Like this is like completely abstaining from elections. Okay, very good. Okay. Yeah. So a lot of people believe it. A lot of people don't believe it. That's very nice. How many of you heard about four colorable theorem for planar graph? So there's a very famous theorem from late 80s, which actually showed this is a theorem. Every planar graph is 4 colorable. Okay, it's a theorem. Every planar graph is 4 colorable. So, of course, if this statement is true, then this is polytime. Okay, then this algorithm is polytime. Right? I check whether the graph is planar or not. If it is planar, yeah, it is 4 colorable. Done. Very good. Okay. In fact, one can construct a 4 coloring in polynomial time. Okay. So for planar graph, let's ask, what about 3 coloring? Is this polytime? Is it NP complete? So we know that whether planar graph is 2 colorable or not is polytime, because it is polytime on arbitrary graphs. Whether it is planar graph is 4 colorable or not, it is polytime because every planar graph can be colored with 4 colors, right? So there's nothing there to check. And in fact, one can construct in polynomial time a 4 coloring of a planar graph. So my next question is, what about 3 coloring? What is known about 3 coloring? Has anybody heard about it? If not, then I will write it down. Okay. Okay. So the known theorem is 3 coloring in planar graph is NP complete. Okay. So now what I'm going to do, I'm going to design an approximation algorithm for chromatic number on planar graph. Okay. Okay. Chromatic number approximation on planar graph. Okay. So here are my steps. I check first, is G 1 colorable? First question. Second step, I ask, is G 2 colorable? Both fails. What I know? G is either 3 colorable or 4 colorable. What I do? Third step, return a 4 coloring of G. Okay. Can you tell me what is an approximation ratio of this? Approximation ratio of this coloring algorithm? Number of colors used divided by the chromatic number of G. Okay. So when can we go wrong? So maybe the chromatic number of the graph is 3, right? But the number of colors used is 4. This is the only time I'm giving an approximation, because if G is one colorable, that is independent set, I check and I return one coloring. If it is not one colorable, then I check whether it is two colorable or not, whether I test whether planar graph is bipartite. If it is bipartite, I return 2, right? And I know it is not 1. So this is also correct. And when it is 3 or 4, I return 4. So it is possible the chromatic number is 3, but I gave 4 colors. So in that case, I had to use 3, but I used 4 colors. But if the number of colors I needed is 4, then I only use 4. That's perfectly fine. Then this is an optimum. So the approximation ratio of this simple algorithm is 4/3 approximation. How many of you understood this algorithm? If yes, please put +1. I have tried to make the parts of the lecture as independent as possible so that you can pick up from whichever portion you wish. Okay. Any question here? Okay. So, okay, like you might be thinking that why am I teaching all this? After all, I was supposed to teach you FPT approximation. And the reason was that I wanted to do the following algorithm. Okay. Okay. So on the planar graph, I can give 4/3 approximation. Yes. Now, what about what is known as K-apex graph? What is K-apex graph? So let me tell you. It's basically it's nothing. Okay. This is a bad color. Let's not use this. G is called K-apex if there exists a set X of size at most K such that G minus X is planar. Okay, so how does this graph looks like? The graph looks like there's a set. Okay, there's a set X. Okay, and here is my okay. I don't know how there could be neighbors like all over the places, but I know that this is a planar graph. Okay. Now, and suppose I gave you this, like there are 2 questions. How to compute X? Okay. Trust me, this is one of the favorite questions in FPT. Okay. And we know how to solve this. Like we know an algorithm that is time f of k n to the power big of 1 can test whether G is K-apex or not. Okay. Suppose, but like my input is that I give you G and I give you X. Like my input, I said, hey, here's my family of apex graph where here's a set X. Okay. Given this X, can we compute good approximation for chromatic number on K-apex graph? Okay. Do you understand the question? So basically, I want to find a chromatic number of graph G, but G has an additional property. For example, additionally, when G was planar, we knew how to do it very well. Now we know very well that G is planar, and there are some X vertices, K vertices, whose deletion leads to a planar graph. Now, my strategy is very simple. Okay, I said, my strategy is that I want to reuse my algorithm on G minus X of planar graph. This is what I want to reuse, which I just now made, right? I just now made a factor 4/3 approximation for chromatic number of planar graph. Okay. So I said, look, to achieve this, what I'm going to do is that so what I'm going to do this is that my strategy is the following. Use different colors or different colors on graph induced on X and different colors on graph induced on vertex set of G minus X, right? So what I'm saying that, look, use different set of colors here and don't use these colors here. So now notice, so what happens then? Okay, then what happens is that for X, there are some independent set which you partition, and for G minus X, I'm going to make at most 4 parts, okay? At most 4 parts. But these are different colors, right? So what is the meaning of this? Like, so now look at any edge. Any edge is either completely contained inside X, then I know that they are across different color classes. Same here. And for any edge which is going from vertex in X to G minus X, hey, that is also fine, because the colors which I use on the graph induced on X and the colors which I use on G minus X are distinct. Okay, so if I follow this strategy up, then I will be very, very good. Okay. Okay. So having a strategy in mind, can you tell me an algorithm to compute chi of graph induced on X in time f of mod X n to the power big of 1? Anybody? Can you design me an algorithm which finds the chromatic number of graph induced on X in FPT time, where FPT in the size of X? Anybody? Pradisa, did you teach them coloring algorithm in your exact exponential time algorithm?
Yes.
Okay.
The dynamic programming.
Yes. Oh, then yeah. What was that algorithm for chromatic number in the exact algorithm lecture of Pradisa? Anybody? What was the running time? So I guess it would have been 3 to the power n, where n is the number of vertices. Like, I'm sure at least this much, and maybe even better, like some 2.2 something to the power n, right? So for now, let's this. Then actually, I can find the chromatic number of my graph induced on X in time 3 power k. Okay. Well, if you don't remember this algorithm, then it's still fine, right? The size of graph induced on X is only k. Try all possible k colorings, or try all possible colorings of graph induced on X. Since size of X is at most k, chromatic number of G is at chromatic number of graph induced on X is at most k. So the function that you need to choose from vertex set of G to 1 to k, like first, like 1 to k prime less than equal to k, is like, how many such functions are there? Well, correct. Agreed. So Dolly has written that algorithm, right? If X was k, right? First color X into power k time. And if you follow my bad strategy, you will get k power k algorithm. Like, I mean, if you don't remember the DP algorithm, then you see, hey, let's enumerate all possible colorings, which is nothing but all possible partitions check whether each part forms an independent set or not. You are done. Okay. So now I'm going to do this. So I'm going to return. So first color this, if right, then in poly time color G minus X, which is planar. Fine. Now, so I have returned. So what is? So I have returned chromatic number of graph induced on X plus some number L for planar graph. Okay. So I'm returning. So what is the number of colors used? Let's ask. Number of colors used is chi GX plus at most 4/3 times chi of G minus X. Is that correct? Right? Now notice this is less than equal to what is the chromatic number of graph induced on X? It is only less than the chromatic number of G. So it is less than equal to chromatic number of G. Chromatic number of G minus X is only less than chromatic number of G. That's great for me. So it is 4/3 times chromatic number of G. So it is 1 plus 4/3 approximation for chromatic number of G, right? Which is equal to 3 plus 4, 7/3 approximation for chromatic number G in apex graph. Okay. And running time was 2 power k. The best running time that we can hope to get is actually 2 power k into the power big O of 1. Right? And the bad running time which I made for you is then k power big O of k into the power big O of 1. Okay. So in FPT time, for this family of graph, we can get 7/3 factor approximation. And trust me, chromatic number is one of the hardest problem to approximate in polynomial time. Right? So when we start to combine the ideas from FPT world, so notice that chromatic number problem was like, chromatic number problem is not even FPT on planar graph. Right? Because 3 coloring is NP complete. So we cannot hope to have any FPT algorithm here on even a planar graph for chromatic number parametrized by number of color. But this strange combination of slight approximation algorithm on planar graph and power of FPT for the modulator X, whose deletion leaves me planar graph, we were able to derive a 7/3 factor approximation algorithm in 2 power k poly n time. Okay. So this is a place where I will take a minute break. So if you have any question, please ask before I give you my final example of the day, if I will have time. Otherwise, I will build something towards that final example. Okay. At what point we say that we cannot improve approximation? Avi, could you unmute yourself and ask your question a little bit better? I'm not able to understand your question.
Yes, sir. Sir, at what point, like, we can say that we cannot improve the approximation from here on, like for this k apex planar this k apex graph, we say that 1 plus 4/3 is the approximation.
Okay.
So what will be the best?
So notice first thing first. Okay. Maybe we could improve slightly better, but notice that can we do better than 4/3 approximation for this? That seems very hard to me. Okay. Why? Because in fact, look at our reduction. Okay. Look at even FPT algorithm, or for that matter, planar, ask yourself, can I have an approximation for planar graph which takes, say, can you tell me a number which is better than 4/3? Say 1/2 approximation. Okay. Okay. So you ask yourself, do you think a planar graph can have 1.2 approximation in poly time? What bad can happen if for chromatic number we can have 1.2 approximation in planar graph? So if the graph is 3 colorable, right? What will I return? Oh, the number of colors that you need to use will be given by how much? 3 into 1.2, which is 3.6, right? Am I right, Avi?
Okay,
so,
okay.
Right? So look, I have an algorithm for planar graph, and I'm guaranteed that it returns me 1.2 factor approximation to the planar graph. Okay, I can check whether the graph is 1 or 2 colorable or not. No, I know whether it is 3 colorable or 4 colorable, but which one I have no idea to decide. But I said, okay, I have this great poly time a polynomial time algorithm, a approximation algorithm, which gives me 1.2 approximation for chromatic number. I said, let me run. It returns me, suppose it is 3 colorable, then it will return me what? How many colors can it use? 3.6. Is 3.6 a color?
No.
So what will it return?
Or it will return 3.
Coloring of my graph. So what can I infer? This is a 3 colorable graph.
Oh,
right?
Yes. Yes.
So this is how you show like that in poly time, why I cannot have certain kind of approximation, right? Same reasoning we can say it cannot even have an approximation of factors up to like 4/3 minus epsilon, because by 4/3 minus epsilon, it will return me number of colors which is exactly less than 4. Right?
Oh,
right?
Okay.
So the moment it is returning you less than 4 colors, I'm happy. So any approximation algorithm should have ratio at least 4/3, and I have shown you an algorithm with ratio 4/3. So this is how you show. So if you are able to come up with a reduction which creates some amount of gap between yes and no, then you use that gap to say certain factor approximation is not guaranteed, and the running time is just running time, like okay, whatever the world you are living in. Does that answer your question to some
Yes.
extent?
Yes.
Okay.
Thank you.
Okay, welcome. Okay. So now I want to go away from this world of chromatic number for a minute. And the reason why I use chromatic number, because you are able to determine that for this problem and approximation algorithm, like what you call FPT algorithm, is not possible to parameterize by chromatic number. But now I really want to talk about hardness in FPT. Okay, so I'm going to build my theory from hardness build my theory for hardness. Okay, and I'm going to build my theory like an engineer. That a problem does not admit f of k n to the power big of 1 algorithm if and only if, okay, if and only if, not if and only if, okay, if there is a reduction from my favorite problem to click problem. Okay, what is the meaning of this? Let me explain to you. So first of all, do you know what click problem is? Click problem in FPT world is as follows. G comma K question is, does G has a click of size at least K? Okay, and I'm going to assume that this problem, this is my assumption. What is my assumption? There is no algorithm for click running in time f of k n to the power big of 1. Okay, there is no such algorithm. Is my assumption clear to all of you? Right? I'm going to assume that click cannot have an algorithm with running time f of k poly n. Okay. Do you know p versus np? Do you know on what basis? What is the such? Do you know that NP completeness theory also has such an assumption? Do you know which problem is this? Anybody? Okay, so that's your homework if you don't know. Okay, so question for you to do Google, check in your literature book. What is an equivalent assumption? Yes, very good. Circuit satisfiability. Equivalent assumption for problems that are in NP. Okay, so Abhinav Chakraborty has written an answer. That's correct. That's circuit satisfiability. Okay, and I'm going to build my theory for you around click. Okay. 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 I have not defined what reductions are. We will figure it out. Okay. What do you think? I mean, there's absolutely no need of, we will see what it means. Okay. Input is GK. Parameter is K. Question is, does G have an independent set of size at least K? What do you think? Is independent set FPT? Anybody? What do you think? So look, in the reduction, the meaning is, or in the world of this, you should always associate the following meaning, okay? If independent set has an algorithm with running time f of k n to the power big of 1, then I can make one for click. This is the only thing that you should remember. And if you remember this, okay. So, okay. So if this is a what, I said, okay, fine. So now suppose I had an algorithm for independent set. Held by independent set takes its input g comma k, and in f of k n to the power big of 1 time returns whether g has an independent set of size k or not. Okay. Now I would like to solve click with the help of algorithm A. Can you help me? Anybody? So for the click, I have an instance G and K. I want to know whether G has an independent set of, G has a click of size K or not. But I only have an algorithm for independent set. How can I use? Very good. All of you are so bright. Say, so all of you are telling me that hey, you feed A, you are given input G comma K, you feed actually G bar comma K, where if there is an edge between a pair of vertex, you delete it. If there is no edge, you put it. Okay. And you feed A. Now, if it says yes, then you know that G has a click of size K. It says no, it means there is no independent set of size K, which implies no click of size K in G. Okay, good. So how much time did we take to algorithm? Let's try to understand. So the time we took, so given an input GK, we first made this transformation. This transformation took time n to the power big of 1, because all we took G. And then on this transformed instance, we ran the algorithm of A, which took time f of k n to the power big of 1. Excellent. Done. Okay, so all of you know that click is hard. Hey, what about vertex cover? Let's go back and let's design such an algorithm for vertex cover. Okay. What I want to solve vertex cover with help of A. Can you think of something? So here also I got a G comma K, right? And here is my that algorithm A. which will take me, and it will tell you it has independent set of size greater than or equal to k or not. This is what it returned. So what will I do if I wanted to solve a vertex cover? Anybody? Do you think? Okay, very good. Okay. So what will be? So what graph will you take? So you will feed A, same G, and you put K prime where prime I ran this algorithm A. Now this algorithm ran in time f of n. So first of all, this transformation takes n to the power big O of time plus f of n minus k n to the power big O of 1. Question to you. Is this an FPT algorithm? Because why? Because absolutely there is no way I can write f of n minus k equal to g of k, right? Doesn't look possible. Doesn't look that this is possible for some g. Okay. So what criteria should be put? Okay. So now we have to think about something, no? Okay, so it went wrong because I had a parameter k, and the new parameter k prime which I constructed, it became function of input. So all went wrong. So what should I demand from k prime? K prime should only be what? Then we have to put some restriction on k prime. Now what should be the nice restriction? Right? So nice restrictions say put, oh, k prime is some function of k only. Exactly. Then what happens? Now let's go back. So if I had some g comma k, I took some poly time and I giving some g prime, k prime, then this is fine because n to the power big O of 1 plus f of k prime times n to the power big O of 1, which is same as n to the power big O of 1 plus f of h of k n to the power big O of 1, right? So this is still a function of k and I'm very happy. Excellent. Okay. But now I still ask myself, why do I need to take running time g of k when I construct this instant g of k in poly n time? Maybe if I look at this, I say, hey, look at this poly n time. Why poly n time, man? Let's make it q of k times n to the power big O of 1 plus some f of k prime n to the power big O of 1. Then this is still looks to me fine because n to the power big O of 1 is fine. This is like q of k plus f of h of k. This is still a function of k, right? So the way to derive a reduction in any world is, what is my hard problem? Okay. Other problem is hard, meaning, look, if for the other problem I had an algorithm, then I can design an algorithm for the hard problem. That's it. Okay. Now, what kind of running time am I allowed? Oh, this is the kind of running time allowed. If this is the kind of running time allowed, so then that is the kind of running time I'm allowed to use when I'm transforming an instance of this problem into that problem. Okay. And things of this nature. So nobody needs to know what reduction definition is. You only need to be aware of or sensitive of what kind of running time you're allowed to run into. And that's it. Okay. Is the idea clear? I'm not going to define what FPT reductions are. For me, this is an FPT reduction, right? That I would like to, given an algorithm, I would like to solve my click problem with the help of this problem. So how much ever allowed running time is, I'm happy to take that to get an algorithm or get the running time of particular form, right? So that's it. Okay. So I have 8 to 9 minutes left. Okay. So is this notion of hardness clear to you? Okay. Clear? If it's clear to you, then put +1. Okay, very good. Notice in polynomial time, this is why every team, like when you do many-to-one reduction in NP complete test, instance must take poly time, because that is the only allowed time. And if that is the only allowed time, the parameter can only be poly. So that is why it is poly to many-one reduction. Right? So if I would have been allowing some other form of running time, then say, hey, to make a transformation from here to here, you're allowed to have that kind of running time. And then you're allowed to have that kind of running time to solve the instance of your problem. Okay. So this is the whole thing that I wanted to tell. Okay. So why did I build all this theory? Okay. I built this theory because I wanted to state a problem, which is a cousin or brother or sister, whatever you want to call it, of okay. So here is called cousin of vertex cover. This is called partial vertex cover. Okay. And you will understand why it is called partial vertex cover. My parameter could be either k, or could be t, or could be k plus t. Okay. These are my 3 potential parameter. Parameter 1, 2, 3. But the question is saying, does there exist a set S, subset of vertex set of G? First of all, cardinality of S should be at most k. Okay. And number of edges that are incident on a vertex in F, or also called covered by S, is at least T. Okay. Now notice that when T equal to E of G, what is this problem? Hello? What is this problem when T equal to whole vertex set? A whole edge. This is precisely vertex cover. Okay. Everyone, correct. But what is this problem tell? This is why it's called partial vertex cover. I say, look, I give you a budget, K. I don't want to cover all the edges, but I would like you to cover, say, at least T edges. So they also like, yeah. So this is the version we are asking, and this is called partial vertex cover problem. Okay. This is like, if you have seen in approximation algorithm, right? Like you're given sets and you are given a number K and say, hey, with K, cover the maximum number of sets possible with K, right? So it is of this flavor, this problem is, okay? Okay, very nice. Excellent. Okay. Okay. So now my first theorem, or among my several theorems, here's my theorem. I will give you a construction. I will convince you that this is correct. And then I will ask you to convince yourself, and then we can meet tomorrow and this. So partial vertex cover does not admit f of k n to the power big O of 1 time algorithm. Okay. So I'm going to show to you that, look, if partial vertex cover has such an algorithm, then we can make an algorithm for independent set with running time f of k n to the power big of 1. Okay. And we have already shown here that independent set cannot have such an algorithm by reduction from the reducing click to it, right? Remember, we gave a reduction, right? That if independent sets have such an algorithm, then click will have such an algorithm, right? So that implies that independent set also cannot have such an algorithm if we assume that click can such a. So this is how you build this complexity family or set of problems which are equivalent under each other with respect to the reduction, like all of these are equally hard. Okay. Now, so rather than showing directly reduction from click, reduction to click, I'm going to give a reduction to partial vertex cover, independent set from a reduction from independent set. So here's my reduction. Okay. So I have an algorithm. Here's my algorithm for partial vertex cover. He needs to take input G, K, and T. Okay. So now I have a independent set instance G, comma K. I do something to it. Okay. So what I do, so suppose I have this is my graph. Okay. Okay. Now, okay, so let me do something concrete so that you will understand. Okay. Let me not be hand wavy. Okay, so this is my G. Okay. Okay. Okay, fine. Let's see if I can write something. Okay, fine. Okay. Okay. What is the degree of this vertex V? What is the degree of V in this graph? Anybody? Degree of this vertex V in G? 2. Very nice. So if it has a degree V, so my process is very simple. It adds, given a graph G, it adds for every V in VG, add n minus, where n is cardinality of VG, minus degree of V pendant vertex. This is what it adds. So how many vertex we have in this graph? 1, 2, 3, 4, 5, 6. Okay. And degree of V is 2. So how many vertex should we add as a pendant? We will add 4 vertex as a pendant. So 1, 2, 3, 4. 1, 2, 3, 4. Very nice. Okay. Okay. So for this also we will add 4. For this also we will add 4. 1, 2, 3, 4. Okay. What is the degree of this vertex? Say degree of W. What is the degree of W? Five. So let's, how many edges should we add? 1 edge. Okay. So we will add 1 edge. And here it has a degree 1. So we will add 1, 2, 3, 4, 5. What is the property of the old vertex? Every vertex after you do, every old vertex has degree exactly equal to n. That's a property of this graph. What is the property? Notice 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Oh, it was wrong. It has degree 3. We should have been only adding 3. So every vertex has degree equal to 6, which is same as vertex set. So this is how we constructed this. Now what I'm going to say in this graph, okay, fine. You constructed, given GK, you constructed G prime, K is going to be K. And now T, I'm going to write K times vertex set of G, or K times N. So what I'm saying to you, cover K n edges. So forward direction is obvious. if G has an independent set of size K, okay, independent set of size K, right? Then how many number of edges which are incident to these guys, right? They have n edges incident to this. Every vertex has n edges, and since it's an independent set, you're not going to double count the same edge, right? So the total number of edges that are incident to these vertices is exactly equal to K times n. So forward direction holds. In the reverse direction, you say, okay, look at a solution here. First of all, you have to show that it cannot contain that pendant vertex, because if it contains pendant vertex, then like you can never cover K and edges. So you will rule that out. And then you will say, look, it has to cover, you cannot have an edges here, because the moment if you have an edge here, then you cannot meet the budget of K. Okay. So this is how you can show that the reverse direction holds, right? So we can show that G has independent set of size at least K, if and only if there exists at most K vertices that covers at least T edges. Okay. So I think this is the right place for me to stop. I have given you an outline of the reduction. I have given you a hand wavy argument why this proof is true. But this is a good exercise for you to think through this reduction, and come back tomorrow and we will start from this reduction and go on to see a couple of more algorithms, couple of more strategy, and do more things tomorrow. Okay, starting from there. I think this is the right place for me to stop the lecture today. Okay, so thanks a lot. If you have a question, please go ahead and ask. Yes.
Thank you, Professor Saketh, for the interesting talk. We are concluding the third day of summer school on algorithm, and tomorrow we will have the session on stable matching in morning by Professor Meghna. And yeah, any question you can ask. You can ask on Julep also, Julep chat.